So unit 7, the entire unit talks about finding area under a curve. Area, not slopes of tangent lines, not instantaneous rate of change. Area. You know area from geometry. Okay? Well, we're kind of going to take some of the stuff you know from geometry, apply some calculus concepts, and we'll be able to solve problem number 2. Problem number 1 was the first semester. Question was asked, what is the instantaneous rate of change of a function, or what is the slope of a tangent? And we knew if we took 2 points, connected them, the slope of those 2 points would be the average rate of change of the function. But if we took those 2 points and placed them infinitely close together, it would essentially be at one location. We could find the slope of that line at that one location, and that would be the instantaneous rate of change, or the derivative. And this is differential calculus. And this was semester 1. Well, semester 2 will be for the second problem. It says take a curve, okay? Any curve. And take 2 points, maybe boundaries, an A and a B. Calculate the exact area under the curve. So find this area in units squared. And this is called integral calculus, and we will tackle this problem this semester. And you will find out by the 4th lesson, actually during the 4th lesson of this unit, how these two problems are related. And you'll actually find out today how we'll be using a calculus concept to find this area, okay? All right. Well, you already know how to find areas underneath functions. Okay, you can already tackle this. Now the key is we're not talking about the area just under, we're talking about like between the function and the x-axis. This is like an x-axis. This is the x-axis. So my function could go below the x-axis. We're just talking about right now functions above it right now. Between the x-axis and the curve. Okay. And the question is, can we find the area under this function? Well, this first one, to find this area, you should be like, yeah, I can find that area. This function is just a straight line, and it makes a triangular shape, and I can find the area using the geometry formula for an area of a triangle. So yes, I can find this area. I can use geometry. And I say the area is just going to be equal to 1/2 the base times the height. The base is 8, the height is 6. And that's going to be 24. Okay, but let's look at the second one, this curve. Well, you do not know that this curve is made up of, you know, regular shapes, like circles, like semicircles, shapes that you have formulas for areas for. We just know it's a curve, okay? It's changing. Doesn't have any straight lines. You can't, as of right now, find the area under this curve exactly, at least using geometry. I'm going to say no, geometry can't help find the exact. Okay? But what we're going to do today is we're going to use our knowledge of geometry, and instead of finding and worrying about the answer to this, you know, problem number 2 above, instead of finding this exact area, what we're going to do is like say, forget about finding the exact area. Let's just approximate the area. Okay? And how can we approximate it? Well, I can use geometric shapes placed on the function or around the function, like a triangle, like a rectangle, like another rectangle. Maybe I missed some, but I pick up somewhere else. Maybe a trapezoid, a triangle on top of a rectangle, and maybe another trapezoid, like that. So I can approximate using a geometry. And this is what we're going to be doing today. We're not going to worry about finding the exact if we have a curve. Instead, we're just going to approximate. Okay, and in this situation, we have objects that we can find the area of, and then we can just sum all of these areas of these objects that we can use geometric formulas for. So I could say that the area is approximately, so area, you can use the squiggly lines for approximate. The area is approximately equal to the sum of my areas. AIs, I'll say, start from my first area, go to my fifth. Okay, that's the idea of what we're going to be doing today. We're just going to take geometric shapes, plop them on top of a curve, and boom, we will have an approximate amount of area that we can calculate. Now, what I did here was good. You know, this will probably generate a decent approximation of the exact area. However, the problem that I have is that I just arbitrarily placed these lines down. I just said, oh, throw this here, throw that there, throw that there, throw that there, and then go from there. Problem with just doing things arbitrarily is that you cannot, you know, repeat that consistently for other curves. Okay, it's not very systematic. It won't be easy to do. You'll just have to look at the curve and then just start drawing lines. So that's a problem if we want to do things easily and quickly. So instead, we're going to do things systematically. There's going to be a systematic process where we're going to use a specific object, so a specific shape like a rectangle or like a trapezoid, and we will use, instead of arbitrary base lengths down here, we will use specific base lengths, and if we do that, these calculations will be easy to do and we'll be able to do them quickly for any of them. Okay, and that process of doing things systematically is called doing a Riemann sum. Okay, Riemann sum, Bernard Riemann came up with this process. It's area approximations under curves using geometric figures. They're typically going to be rectangles and they're typically equal width. You need to be familiar with the word Riemann. Kind of an alternate definition of a Riemann sum is a systematic way of approximating areas. Same shape every time, typically, in this situation, always same width. Same shape and width. Okay? And that's the first thing. Step one for these Riemann sums is this width. Here, all these widths are different. But Riemann says, make it easy on yourself and make all the widths the same. So, an example, if I wanted to approximate the area under this curve, and we go from 2 to 18, and I had to have 4 objects, Riemann would say, okay, make sure the objects' widths are the same. What would be the width of each object? Before, right? How do we know that? Well, we go from 2 to 18. This distance here is 16. So that's the x distance. I divide that into 4. So we know we'd go from 2 to 6, 6 to 10, 10 to 14, 14 to 18. Okay? So that's the first step, is to kind of regularize, normalize, make it easy for us to find our bases. We find the width of our geometric figure, which is also called a partition or a subinterval. Okay? If you're told you're going to use this many subintervals, width of the subinterval, that'd be this many figures. Like, approximate the area under this curve with 10 subintervals. That just means you're going to use 10 objects, 10 geometric objects, 10 rectangles. Okay? Now, you can find it using this formula. However, you will find that you won't need this formula because it's just intuitive, the calculation to find the width of each of these. If you go from 2 to 18 and you want, 8 objects, each of the widths has to be 2. If you're going from 2 to 18, you want 4 objects, each of the widths has to be 4. But this will work if maybe it's not as intuitive. B minus A is just going to be the x distance between your two boundaries, and n is your amount of objects, amount of partitions, subintervals, or shapes. Take that, calculate it, you'll find the width of each shape. Okay? There are 4 types of Riemann sums that you need to be comfortable with. A left, a right, a midpoint, and a trapezoid. We'll do the same example each time to show you and to introduce to you these Riemann sums. They're not hard, as long as you're paying attention. Okay? The left, right, and midpoints are all using rectangles. Okay, the bases are pretty much going to be the same. It's all going to be about the heights. Heights on the left, height on the right, height in the middle. So let's say the heights change. Trapezoid is different. We'll get to the trapezoid when we get to the trapezoid. Okay? All right, here we go. Let's start with a left Riemann sum. Let's learn the systematic process of finding an approximation for the area under a curve using one of these Riemann sums. Okay? There's the definition for a left Riemann sum. You can write it down, or you could just kind of walk through kind of the process that I would show you to kind of draw these rectangles and to calculate this approximation. Okay? Here is the question right here. We want to approximate the area under this function from 0 to 8 using a left Riemann sum with 4 subintervals. Now we're going to use the same example 4 times. The table is going to be used every single time if you want to write that down once, and then maybe sketch 4 different versions of that graph. They don't have to be exact, just approximate sketches, but we'll be using the same one each time so that you don't have to copy multiple tables of information down. But they are very good things to copy down. So I'll give you some time to do that. Graph does not have to be perfect, just a sketch. As long as you, as long as you sketch, you'll be fine. The table is important. Okay. Now, I'll just write this down. Step one for all of these Riemann sums is to figure out the width of your bases, or to figure out your bases of your objects. So it's very, very important to know what the question is asking you. The question here is asking us to approximate this area with 4 subintervals. Since you read 4 subintervals, you know that you're going to have 4 objects. Since it's a left Riemann sum, you know you're going to use rectangles. Okay, so I'm going to use 4 rectangles to approximate the area under this curve. But it's even more systematic than that. Because it's a left Riemann sum, the heights will be very specifically chosen instead of arbitrarily chosen. Okay? So 4 objects, rectangles. We know that if we go from 0 to 8 and we have 4 objects, each object's width is going to be what? 2. Simple, right? Don't all shout it out at once. So the width, which is what we can consider delta x, it's the change in x, is going to be equal to 2. You can calculate that also by just doing b minus a over n. Right? Or just intuitively figure it out. All right, so that means for my rectangles, I can start and figure out the bases. We go from 0 to 2. There's my first base of my first rectangle. From 2 to 4. There's the next rectangle's base. 4 to 6. The next one, 6 to 8. Okay, so I'll call this rectangle 1, rectangle 2, rectangle 3, and rectangle 4. There we go. 4 subintervals, 4 rectangles, 4 bases. You can also do this on the table. Now, if you sketch the table down once, you might want to just kind of write it down underneath, but typically AP-style problems will just give you a table. So instead of having to sketch it down, you can actually just use the table, and you say, here are my bases from 0 to 2, 2 to 4, 4 to 6, 6 to 8. And then we'll be able to figure out the heights from there. Okay? So that's step 1. Now, the heights of my rectangles, since they are left rectangles, are going to be specific. The height is going to be determined by the function value on the left of the subinterval. Okay? What does that mean? Well, let's take rectangle number 2. Here is the base of a rectangle, the base of my subinterval, We will go to the left of this base, and we will go to the height, or the function value above that, and that will be the height of rectangle 2. Right there. And boom, this is the rectangle that I will be using to approximate the area under that function between 2 and 4. Okay? Now, you guys sketch the other 3 rectangles, 1, 3, and 4. All you need to do is look at your subinterval. Since it's a left Riemann sum, you will go all the way to the left of your base, and then you'll go up to its height above that. So here is number 1. I guess this is step 2, is to figure out your heights. For number 3, rectangle number 3, I'm going to go here, this height. And rectangle number 4, go all the way to the left and then up. This would be my height. Okay. And what I will do is be able to calculate the areas of these rectangles, add them together, and that will be my approximation. You'll notice it's not going to be a good approximation. We're missing a lot of space here, but it's just this systematic process that Riemann is telling us to do to find the area under this curve, or to approximate the area under this curve. Okay, now up here over your table, you can see it's easy to do as well. Between 0 and 2, you go to the leftmost. Hold on a second. Between 0 and 2, you go to the leftmost height, and you could circle it to say, okay, 0 and 2, height is 1. 2 and 4, the height is 5. 4 and 6, the height is 4. 6 and 8, the height is 7. Okay, and those are the values we are going to use to calculate the area. The tablet got all screwed up. Area is going to be approximately my base of 2 times my height of 1 plus my base of 2 times my height of 5. This isn't going to work. The thing is, it has to work. Okay, hold on. Pause. Like a business. Sorry, we got a first rectangle number 1 has a base of 2, a height of 1. Rectangle number 2 has a base of 2, a height of 5. Rectangle number 3 has a base of 2, height of 4. And rectangle number 4 has a base of 2, height of 7. Boom. Calculate those, you get the area. Now what you'll find out, since this is systematic, is that it's actually easier than just doing, approximately, these. You can factor out the bases that are always going to be the same and just sum up your heights. So you can sum up 1, 5, 4, and 7. So 6, 10, 17 times 2, you get 34. Or your area is going to be approximately just the sum of your heights, which is your f of x's, times your delta x here. And I'll show you the formula using summation notation. The sum of your f of x's times the delta x. Okay? You'll see this formula moving forward. Okay, that's left. Let's move on to right. Any questions about the left Riemann sum? Yes. Yes. Not about the left Riemann sum. Right Riemann sum. Same process as the left Riemann sum, only the height is determined by the function value over the rightmost point of each subinterval. Okay, so same question, only changing up the type of Riemann sum. Instead of left, we're going to right. We want to approximate the area under this curve using a right Riemann sum with 4 subintervals again. Since I have 4 subintervals, I know that the width is going to be 2 again. That's the delta x. So from 0 to 2, 2 to 4, 4 to 6, 6 to 8. Here are my bases. I want to do it over the table. 0 to 2, 2 to 4, 4 to 6, 6 to 8. Now this time, 4 rectangles as well. 1, 2, 3, 4. You will use the height over the rightmost point of each base. So for rectangle 2, I go all the way to the right, and this will be my height for rectangle 2. You see that? So for rectangle 3, I go all the way to the right of the base, and I use the function value above that for the height of rectangle 3. Here's rectangle 4 and rectangle 1. And we will calculate this area in here, and that would be our right Riemann sum approximation for the area under the curve. Here you would circle the 5, the 4, the 7, and the 7.5. RRS is short for right Riemann sum. We could have used LRS for left Riemann sum. Is going to be approximately 2 times 5 plus 2 times 4 plus 2 times 7 plus 2 times 7 plus 5, 7.5. And again, since it's systematic, we can factor out the 2 and sum up our heights. Nine, 16, 23.5 times 2, so that's 45. Is that right? No, 47, of course. Okay, that's the right Riemann sum. Midpoint Riemann sum. That's what we're going to do. Use the height in the middle of our subinterval. Same question. I'll do this a little more quickly. 4 subintervals. Width is 2. Zero to 2, 2 to 4, 4 to 6, 6 to 8. Do it up here. 0 to 2, 2 to 4, 4 to 6, 6 to 8. And then in this case, with the midpoint Riemann sum, the height will be the function value in the middle of your base. So if this is rectangle 2 again, instead of going to the left or to the right, I go to the middle. And I go up to this middle height. And this would be the height of the second rectangle used to approximate the area under that curve. Okay, middle heights. And up here, you would circle 4, 4.5, 4.5, and 8 as they are in the middle of your intervals. Okay, and then, of course, I'm just going to go straight, knowing that we could factor out the 2, sum up our heights. 9 plus 8, 17 plus 4, 21 times 2, 42. Okay, cool. That's midpoint. Questions about that one? Okay, those three, very similar. It's all about the heights of the rectangles, and left, right, or midpoints will determine it. Trapezoid's a little bit different. Okay? So here's a trapezoidal Riemann sum. The first thing we're going to do to understand the trapezoidal Riemann sums is understand how to draw the trapezoids. If we understand how to draw the trapezoids, we will be able to then figure out how to calculate the area. And this definition may be tough to explain. Just watch and see. All right, how to draw the trapezoids. What you're going to do is you're going to use both points as your bases and then you're going to connect the dots. Now, actually, this is silly of me. I'm not doing step one. Step one is to figure out the amount of objects. Here we have 8 subintervals. So 8 objects, 8 trapezoids. Since there's 8 objects, the width is going to be now 1, which is why we're doing this. Okay, 8 minus 0 divided by 8. The width is 1. So from 0 to 1, 1 to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 6, 6 to 7, 7 to 8. Those are all bases of my trapezoid. The reason why I'm doing 8 in this situation instead of 4 is to show you that the shortcut method that I will show you is very important. Okay, now let's draw our trapezoids. All we do is just use each height from the outsides of our bases, and we'll connect the dots. Okay? Now, you might be thinking, where are the trapezoids? Well, I'll show you. You're used to trapezoids looking like this. And a trapezoid has 3 distinguishing features. It's got a height, it's got a B1 and a B2. Now, does anybody remember the area formula for a trapezoid from geometry back in freshman year?
B1 plus B2 times the height.
That's exactly right. Excellent, Mr. Bracken. Buckner. Keep doing that. Sorry. I always I got it right this time. The area formula of a trapezoid is 1/2 my height times the sum of my bases. Okay, you see this trapezoid and you're like, well, those don't look like these trapezoids. Well, watch. If I kind of turn this object on its side and flatten out a side, I get this. Okay? It's almost like taking this and sliding it over a little bit. Come on. And then flattening out this side. It maintains its integrity as a trapezoid. It has a height and 2 bases, but it just doesn't have 2 of the diagonal lines. If I take this, rotate it, turn it into this. Well, now look, what we are used to having the bottom being our bases, the bottom length is now our height. That's h. And this would be considered a base, and this would be considered a base. So we'd have h down here instead of delta x. In this situation, delta x is equal to h. This would be B1, and this would be B2. For our second trapezoid, we'd have h. We would use B2, and we'd have B3. Okay? So using this area formula, which you should have down, we can sum up all 8 of these trapezoids. Now, I'm not going to write them all down because it's the long way, but I'll show you what it would look like. The area would be approximately 1/2 my height, which is my width or my delta x, B1 plus B2. Well, the first height is 1, the second height is 4. Now, for the second trapezoid, it'd be 1/2 1. I would use the second height and the third height. So I'd use the 4 and the 5. For my third rectangle, 1/2 1. I'd use the third height and the fourth height. 5 plus 4.5. And I would continue to do that until I get to the last one, which would be a height of 8 and 7.5. Okay? That's a long way to do it if you did all 8 separately like that. Since this is a systematic process, watch how things get easier. A shorter way to calculate it is to factor out the 1/2 and the 1. And watch what I have. I'll have 1 plus 4 plus 4 plus 5 plus 5 plus 4.5. 1 plus 4 plus 4 plus 5 plus 5.5 plus 4.5. And if I kept going, it would be plus 4.5 plus 4 plus 4 plus 4.5 plus 4.5 plus 7, 7 and 8, 8 and 7.5. Shorter, but not great. The shortest way to do it, and the way that you will write down and remember for the future, is to realize that you have 2 4s, then you have 2 5s, then you'll have 2 4.5s, then you'll have 2 4s, 2 4.5, 2 7s, 2 8s, and then 1 7.5 and 1 1. So watch what I can do. I can just take 1/2 my consistent widths, which are my heights, take the sum of my first plus my last, and then double the sum of my middle numbers. Okay, and there's your quick area from a trapezoidal Riemann sum. You're going to say it's 1/2 your delta x, your first height, your first height, plus your last height, plus double all of your middle heights. Okay, definitely write that down. That's your shortcut. You will use that fairly frequently. Okay, now that we have this, we now know, when given a table, how to approximate areas under certain curves. Well, I can go a little bit further, and I could give you a function. And you could approximate the area under a function. We want to approximate the area under x squared between 0 and 4 using 4 subintervals. We'll find a left Riemann sum, a right Riemann sum, and our trapezoidal Riemann sum. What I would recommend is you could either sketch or you could create your table. Maybe a sketch on the side just to help us. Here's x squared between 0 and 4. If I'm using 4 subintervals between 0 and 4, what is the width of each of my subintervals? Don't say it too loudly. 1. Okay, so from 0 to 1, from 1 to 2, 2 to 3, 3 to 4. 4 objects, 0 to 4, we know my width is 1. That is number 1. That's always the step 1, figure out your width. Well, you can kind of draw your triangles from there, or you could just create a table and then use that to your advantage. So I know I go from 0 to 4. So here are my x's from 0 to 4. I know my f of x values are just your x's squared. And here we go. If I add a left Riemann sum, we go from 0 to 1, 1 to 2, 2 to 3, 3 to 4. I would use my left heights, 0, 1, 4, and 9. It would look like this. I'd actually have a rectangle with a height of 0 as my first rectangle, second one height of 1, third one height of 4, fourth one height of 9. Okay, and it would just be 1 times 0 plus 1 plus 4 plus 9. Simple. If I had a right Riemann sum, well, from 0 to 1, I'd use the height of 1. 1 to 2, I'd use the height of 4. 2 to 3, 9. 3 to 4, 16. Okay, so I'd have here, 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 and 16 up there. Those being my rectangles. So we can say, okay, consistent width of 1, heights of 1, 4, 9, 16. Finally, the trapezoidal Riemann sum. Using your formula, you'd have 1/2 your consistent width. In this case, it's 1 as well. Use your formula, just your first height plus your last height plus double your middle heights. And there you go. Now, we can kind of see by looking at our graph that these approximations are not going to be good, right? But using both approximations, a left and a right, we can actually get a really good idea of exactly what our value is. And that's because I know the left, looking at my rectangles, is going to be an under approximation. I'll change that to blue. And I know the right is going to be over. So that means the exact has to be somewhere in between. 9 plus 4 is 13, plus 1 is 14. 1 plus 4 plus 9 plus 16, so that's 25, 29, 30. Okay? It's got to be somewhere between 14 and 30. The trapezoidal Riemann sum will also do a good job, and you can actually see by using the pictures that since this is concave up, the trapezoidal will also be slightly over. Okay? So that's good information to know. We know that the actual area has got to be between 14 and 30, and it's got to be just underneath whatever this value is. I'm not going to calculate it right now. Okay? Good. Keep that in mind over approximations, under approximations moving forward. But now let's move on. Don't do this again. Okay. You see the left Riemann sum, you see the right, the midpoint, the trapezoid. Which one do you think is the best? Looks like the trapezoid, right? Looks like the trapezoid is really, really close, and the left and the right and the midpoint are garbage. Okay? Turns out they're all equally as powerful. They all can be equally as accurate. They're all pretty much the same. Okay? And it deals with one condition. Like, what can I do to the left Riemann sum to make it closer to the actual average, the actual area, and closer to what the trapezoid is going to give me? What's the condition that will make that left Riemann sum better? Exactly. Increase the amount of objects that I'm using. Okay? So if I used 8 rectangles here, or let's say I use 16 left rectangles, all of a sudden if I use 16 rectangles here, it's probably going to give me as close as a value as using 8 trapezoids. Okay? So that's important to know. More rectangles, the better the approximation. Okay? Well, could I use 32 rectangles if I had enough information? Sure. Could I use 100 rectangles? Sure, if I had enough information. Could I use 1,000 rectangles? Yes, if I had enough information. Well, 1,000 left rectangles and 1,000 trapezoids are pretty much going to give you the same value. So all of a sudden, what seemed much better than the other, which one seemed much better than the other, now they're about equal. Okay? So it turns out we're just going to talk about left Riemann sums moving forward to get this exact area. I'm not even going to worry about trapezoids unless I wanted to approximate. Okay? And changing things from approximations to exact values, that's a key to the next step in this class, to find the exact area. If we have this curve and I asked you what if we wanted a more exact approximation for the area under the curve, what can we do? We would say add more objects. And let's say we use our left Riemann sum formula. That's what we're going to use. All it is just the sum of a bunch of function values, we'll call them f of xi's, times a bunch of widths, delta x's. And we say the I started at 1 and went to n. And we know that delta x is just the the b minus a over n formula to find the length of our partition, our subintervals. Okay? So this gave us a approximation. And if I had 10, I'd put 10 here for the amount of rectangles, and this would be 10. If I had 20 rectangles, I'd put a 20 here, and I'd put a 20 here. If I had 1,000 rectangles, I'd have 1,000 here and 1,000 here. Turns out, what we want to get the exact area is how many rectangles?
Infinite.
Yes. What we want to do is put as many rectangles, or an infinite amount, we want to approach an infinite amount of rectangles, and add up the areas of all of those rectangles that we can find, and all of a sudden what started as an approximation turned into an exact. Just like how if we took 2 points and connected them and find the slope, that was the slope of a secant, that was an average rate of change. If we made those 2 points infinitely close together, not on top of each other, because you can't find the slope of 2 points on top of each other, but infinitely close together, then all of a sudden you can find the slope of those 2 points, and it essentially would be the slope at an exact point. It's the same idea here. Instead of infinitely close together points, we're talking about infinitely skinny rectangles. Okay, so what would I change in this formula to go from an approximate area to an exact area? Yes, we'd put an infinity for n, right? But we don't want to plug in infinity into that summation formula because we can't really grab infinity. So we need to talk about as n approaches infinity, and what is the notation that we use to say as something is approaching. The limit, exactly, good job. So the exact area is now this formula, and you should write this down. The limit as n approaches infinity of the sum of all of these function values, which were the heights of rectangles, now times these widths. Now as n approaches infinity, what happens to b minus a over n? It's very, very small. Essentially what? Essentially 0. Now we're not going to put down 0 because there has some value. It's approaching 0, but it's not exactly 0. What notation do we use instead of a overall change in x to turn it into an instantaneous change of x? The derivative, kind of, it's the d. It's not like dy over dx. Remember with slope of a secant, it was delta y over delta x. And if we want the instantaneous rate of change, it's the instantaneous change in y over the instantaneous change in x. So we use dx. And we don't want to think of that as the derivative, more of like an instantaneous change. So this becomes dx. Okay, this is the concept, the theoretical concept behind finding the exact area under the curve. We'll take an infinite sum of skinny rectangles with heights based on function values and widths that are going to be infinitely small. This leads us into the notation that we are going to be using a lot the rest of the year. It's called the integral notation. Okay? Mathematicians did not want to write the limit as n approaches infinity of the sum as I starts at 1 and goes to n every single time. It became annoying to do. So they said, let's take this part of this formula and shorten it. And let's make it a tall, skinny f. Okay? This is called an integral. It is an infinite sum. It can be used in different applications of things. In this situation, since we're using it to find the exact area, we're going to take an infinite sum of heights times widths. And now that we have these heights and these widths, this integral with f of x and dx in it becomes the exact area. That's another meaning to it. Now, it's actually not done yet, because with that delta x, we knew that it was b minus a over n. The b and a helped us kind of define our boundaries. We need to define our boundaries here as well, so we will put the a and the b here. This is read the integral from a to b of f of x dx. Translation, it is the area under f of x above the x-axis between a and b. I mean, it can mean multiple things. This is the first statement. It can mean the infinite sum of rectangles with height f of x and a width dx, or it could mean the area between the x-axis and f of x from a to b. Okay? That's what an integral is. It's an infinite sum. It stands for area if you have f of x and dx next to it. Now, knowing that notation now, you can answer some problems without knowing of how to find integrals of curves, or how to find infinite sums of curves. Instead, if I give you a straight line, here's a straight line. This function is f of x equals 2. And ask you to find the integral from 0 to 3 of f of x dx. Well, that's the infinite sum of rectangles with height f of x and width dx, infinitely skinny. Or it's what's the area between the x-axis and the curve from 0 to 3. Well, since it's a straight line, you could do this. You can say, okay, what is this area? I can use geometry. It's just going to be base times height. 6. You can already answer problems with integrals in it. Something like this. Simple. From 0 to 3, the triangle, 1/2 base times height. Simple. You can do that. because you know the interpretation of this. The integral from 0 to 3 means the infinite sum of infinitely skinny rectangles, or just the exact area between the x-axis and the curve. Now, something to note, and this is where it gets tricky to say that this stands for the area. What if our curve or our function went under the x-axis, say from 0 to 2 here, and my curve is here? Your geometry teacher would have told you that area is always positive, right? If you have an area, it's got to be a positive area, okay? So if you look at this area, you would say, oh, this is just a triangle, height 3, base of 2. This is going to be an area of 3. This is where it's a little tricky. This is where we have to go to that other interpretation of it's an infinite sum of function values times height. This function value right here, what's the function value? -1. This is -2. This is -3. All of these function values are negative. Hold on. Well, if we're taking an infinite sum, these f of x's are all going to be negative. But the dx, the width, is all going to be positive. All of a sudden, this is a negative area. Now, you might be saying, well, should I think that it's going to be positive? All I'm going to tell you is, from now on, for this class, your function's underneath the x-axis, consider it a negative area. And that's okay, because it's a negative, infinite sum, negative function values times width. And that's fine. There are going to be a couple more examples on the video that you should watch so that you have a full understanding of this stuff. But we've pretty much covered everything, okay? All right, now I can ask a similar question for this. I can say from -1 to 2 of f of x dx. So written this way, it means exact area. If I start at -1, though, we'd have to add the area here to the area here. So since it's below the x-axis, these function values are negative. We consider this to be a negative area. I would have to add this positive area here, which would be just, you know, from left to right, 1/2. The base is 1, the height is 1. So that would just be 1/2. I'll just write 1/2. So I would have that positive area above the x-axis and then the negative area below the x-axis, giving me my answer for the area between -1 and 2. Now we could ask questions using line segments. Here we want to find the integral from 0 to 2, from 0 to 5, and from 0 to 7. So it's just talking about, you know, adding up all of these areas together from 0 to 2, and then from 0 to 5, 0 to 7. And that is what we would consider this, exact areas, and we can find it since these are straight lines. So from 0 to 2, this is a trapezoid. It would have a height of 2, a base of 1, and a height of 1, a height of 2. You got to start being familiar with looking at these figures and noticing that they are trapezoids. That makes calculations easy. This is just going to be 3. From 0 to 5, I would be adding this rectangle here, or I could consider this a trapezoid with this height of 2 and a base of 3 and a base of 2. But instead, let's just say this is a 2 by 2, and this is a 1/2 base of 1, height of 2, so that's 1. So I got 3 plus 4 plus 1, that's 8. And now from 0 to 7, I have this area here. It's a base of 2, height of 2 triangle, so that would be a 2. However, since it's below the x-axis, we consider that area to be negative, since those heights are negative. The f of x's are negative. So I have 8, and then I would just add the -2 to get 6. Okay? Okay. Last thing to talk about is just over and under approximations. We mentioned it before. Just to kind of sum things up, let's say I have some function that is increasing. I'm just going to throw this out here. Okay, this function is increasing. We should be able to figure out if a left Riemann sum or a right Riemann sum is over or under. Okay, now the way I can do this quickly, if I just know that a function is increasing, I can draw an increasing function no matter what. You know, it don't matter how I draw it. I can do concave up like I showed. I can do concave down. I can do a straight line as long as I know that it's increasing. What I do is I like to, you know, make one or two subintervals. This is just two subintervals. A left Riemann sum would go here and here. And no matter how I draw this increasing function, we should notice that my rectangles are all going to be under my actual area. So let's draw something that's concave up. Watch how this is under, and this would be under. That's a left Riemann sum. So a left Riemann sum is under if f prime is positive, if the function's increasing. A right Riemann sum, conversely, would be over. You can kind of see that by drawing, if this is my subinterval from A to that value, here would be my first rectangle, which would be over the actual. Here would be my second one. And it does not matter if we are concave up or concave down. We are going to be over. Now you'll see if f prime is negative. Let's just go ahead and change things up a little bit. So let's say we're going like that. That's a negative f prime. That is a function that is decreasing. I can try my left Riemann sum and my right Riemann sum. It's important, if you have questions that just give you this information, that you can draw something and then draw some rectangles, and that will help you out. So let's talk about a left Riemann sum. I'll use two bases from here to here, here to there. Here's my first base right there. Here's my second base and my second height. So those are my two rectangles. It's definitely going to be over. Conversely, the right Riemann sum we can find is under. Okay? Now, you probably are wondering about a trapezoidal Riemann sum. Well, trapezoidal Riemann sums, and I'll actually kind of start over, deal with concavity. If we know the concavity and if a function is increasing or decreasing, we can figure out if a trapezoidal Riemann sum is over or under. Let's take something f prime that is positive and double prime is positive, so we are increasing concave up. If I took a trapezoid, say from here to here, and connect it, we see that straight line would be just over. So if we know the concavity everywhere, we know that this is going to be over. If f double prime was negative, you would see that it would be under. Let's change that to negative. Let's start over. Here would be concave down, trapezoid, connect the dots. You'd see those straight lines would be under the actual. Something like that. Okay? So the concavity would help you determine that the trapezoidal Riemann sum would give you an under. Now, if you don't know the concavity, then you don't know. So let's say I have a function like this, and say we change concavity or something like this, and we're doing a trapezoidal Riemann sum. Well, in this situation, it looks like it could be exact. You know, who knows? Is it over? Is it under? I'm not sure. So in this situation, we're not sure. So as long as we know if something's increasing or decreasing, and we know the concavity is consistent, we can tell if a trapezoidal Riemann sum is over or under. Okay, that's it. Hope you work on your homework, understand it, and come in with questions if you have any. Thank you.